Hello dear students, so I'm back with our B2S series. We are currently doing magnetics and we are today starting the third lecture. In the previous lecture we learnt about magnetic field produced by conductors of various shape, and we talked about a straight segment and we also talked about an arc. How much is the magnetic field produced by an arc? So we talked about this. Today we are going to discuss that once we know the magnetic field, let's say we know how much magnetic field exists in space, then if a charged particle moves through that magnetic field, how much force acts on that charged particle. So our today's topic would be force on, rather I should write magnetic force. Okay, so magnetic force on a moving charged particle. Okay, so this is our agenda for discussion today. So let us assume that in some region of space there is a magnetic field that exists. Okay, and there is a particle of charge q which is moving with a velocity v. Okay, so by doing a lot of experiments, okay, yes, Damodar Maji, it is live. So by doing a lot of experiments, okay, it has been confirmed, after trying all the possibilities and then observing how the particle is getting affected by the magnetic field, the magnetic force on this particle is written as Q into V cross B. So this is the formula which gives us the magnetic force acting on the particle. Now from this formula there are a lot of conclusions that we can draw. For example, we can see that this force involves cross product of two vectors, that is the v vector and the b vector. Okay, and the result of a cross product is perpendicular to both the involved vectors. Okay, so this means that the force will be perpendicular to v vector as well as b vector. So it is going to be perpendicular to both vectors. Now because force is perpendicular to v vector, it means that the power, which is actually the product of force into velocity, would be zero. That means this force cannot do any work on the moving particle, which also means that the kinetic energy of particle, because if there is no work, the kinetic energy will not change. So kinetic energy of the particle remains same. Okay, it remains same, which also means that the speed of particle, okay, speed of particle remains same. So we now know that magnetic force, okay, cannot change the speed of the particle. Okay, so speed of the particle remains same. So very important, very straightforward conclusion, but very significant conclusion. Okay, so a magnetic force cannot change the speed of a moving charged particle. Okay, apart from that, let's consider various possibilities. Okay, so various possibilities of force, okay, or various possibilities of trajectory, we can say. So let's talk about that. Okay, so the first possibility is that what if the v vector is parallel to b vector, or let's say anti-parallel. So parallel or anti-parallel. So we are considering the case when theta is either 0 degree or 180 degree, where theta is the angle between magnetic field and velocity. Okay, so let me draw some field lines. So let's say that this is magnetic field, okay, which we are indicating by lines, and these are equispaced lines parallel to each other. So magnetic field is uniform, and let's say there is a charged particle. Okay, let's say there is a charged particle which is either moving in this direction, or let's say this is moving in this direction. In both the cases, in this case theta is 0 degree, in this case theta is 180 degree. So in both the cases force will be zero. Why? Because if we check the magnitude of force, we should be writing as QVB sine theta, and sine theta is 0 for theta equal to 0 degree or 180 degree. So in this case the force will become 0. So the particle moves undeviated. The speed, we already checked that the speed cannot change. Now we are saying that there is no force, so no deviation will also take place. So this particle continues to move in a straight line. So in this case, if we talk about the trajectory of the particle, it would be a straight line. Okay, some simplest of cases we can say. Now next, let's just consider another special case, and then we'll move on to a general case. So next, let's talk about the case when velocity is perpendicular to magnetic field. Okay, let's consider the case when velocity is perpendicular to magnetic field. Okay, so let's see what happens in this case. So mathematically, in this case, we are considering theta is 90 degree. Now, let me first indicate the case. So let's say we have a magnetic field which is going into the screen. All right. So in science, in general, when you have to show a direction going into the screen, you use crosses. So all these crosses, they indicate magnetic field lines. So every cross is one magnetic field line, and cross indicate a field line going into the screen. If we want to represent field line coming out of the screen, that would be done by dots. Okay, so dots represent field lines, or any direction coming out of the screen, and cross indicate going into the screen. Now let's say that this is a charged particle and we have given it a velocity v like this. Okay, now we want to predict that what will happen. So guys, first of all, we need to check the direction of force on this. So in this case, because the angle is 90 degree, force will certainly be non-zero. We need to check the direction of force. Now to do that, let me first teach you something else. Like, let's go back to this definition. Okay, so from this definition, it is very clear that the direction of force would match with the direction of V cross B. Okay, now let me show you a technique which you can use to readily determine the direction of force. For example, let's take a case. Let's take the this case. Okay, so magnetic field, suppose if it is in this direction, and suppose if the velocity is in this direction. Okay, so we know from cross product property that V cross B will be into the screen. Now that is one way to determine the direction using the property of cross product. The other way, which you will find easier to do in this particular case, let me teach you that. So you have to use your right hand. Okay, you have to use your right hand, and now your right hand has 4 fingers and 1 thumb. Okay, so multiple fingers and a single thumb. Now generally, while making the drawings, we use multiple lines to represent magnetic field, but a single arrow to represent velocity. So that will be your cue. That will help you remember what you need to do. Multiple lines will represent what we use, what we use to represent by multiple lines. So magnetic field. So field lines, your fingers will represent magnetic field. Your thumb will represent velocity. Okay, so in this case, field is in this direction, velocity is upward, and then force will, for a positive particle, the force will be in the direction of palm. Okay, and for a negative particle, the force will be in the direction of back of palm. So here magnetic field is like this, velocity is upward, so force is inward, because we are considering a positive particle. Had this been a negative particle, then magnetic field would have been like that, velocity upwards, and the force would have been outward if this were a negative particle. Okay, so very easy to remember: magnetic field lines, velocity, and then force. This one, force. This will help you remember. So positive particle means slap from the front of your palm, and a negative particle would mean a slap from the back of your palm. Okay, now with this, if we come and check here, okay, so magnetic field is inward. Okay, magnetic field is inward, velocity is in this direction, so the force acting on the particle is upward. So what this force will do, this force will deviate the particle upwards. Okay, so the particle wanted to go straight, but because of this force, it will probably end somewhere here. Remember, the speed cannot change. Okay, so now the velocity, the same speed, is in this direction, though the particle has deviated a bit. Okay, and now the force, if you check, now the force will be in this direction. So force is always perpendicular to the velocity, and because of this, again, the particle will not be able to travel straight. The particle will probably end up somewhere here, and now the force will be like this. So I hope you are able to imagine what kind of trajectory it is turning into. So it is turning into a curved trajectory. Okay, and if you do the math a bit, you will discover that it actually turns it into a circle. Okay, the magnetic field is present in this region also. I did not draw the magnetic field there. Okay, let's do it now. So everywhere the magnetic field is present. Okay, so this particle will start moving in a circle. Okay, and all these forces, they will point towards a common point, which will become the center of the circle. Okay, let the radius be r. So in this particular case, which case? When velocity is perpendicular to magnetic field, in this particular case, the trajectory is circular. All right. Hi Bhagwan Patil, good evening. Okay, now let's do some math. If it is moving in a circle, we would like to know that what is the radius of the circle, what will be the time period of circular motion, what is the angular velocity, and things like that. Okay, so let's first talk about the force acting on the particle. The force will be given by, like, the magnitude of the force will be given by QVB sine theta. Theta is 90 degree. So this will be QVB. And now because of this force, the particle is undertaking circular motion. So this is the centripetal force, and therefore we must equate it to mv square by r. And from here you will discover that r is actually mv by qb. Okay, so that this formula gives you the radius of the circle on which the particle is moving. Okay, mv by qb. Okay, now this mv can be written as momentum also. Okay, it can be written as momentum. Momentum can be written as root 2mk, where k is the kinetic energy, m is the mass of the particle. And many times to accelerate charged particle, we use potential differences. So the kinetic energy can be written as root 2m q into delta v, where delta v is the potential difference that has been used to accelerate the particle. So I want you to remember this part, but I also want you to remember that we can convert the same expression into a lot of other expression in terms of other parameters. Here is momentum, here is kinetic energy, here is delta v, the potential difference that we use to accelerate the charged particle. So remember all of this. Okay, so this is one of the formula that you need to remember. Now next, let's talk about the angular velocity. So how do we write the angular velocity? Angular velocity is v by r. So r was mv by qb. Okay, so it turns out to be qb by m. Now if you notice that there is something very significant about this formula. All right, and what is that? The significant aspect about this formula is that it is independent of initial velocity or independent of speed. It is independent of speed. Okay, that's actually quite strange. It is independent of speed. What does that mean? Like, what is the interpretation of this? Okay, if it is independent of speed, then what is the interpretation? So let's say there is a magnetic field in this region of space where we are doing whatever we are doing. Okay, and let's say I have a charged particle with a charge q, okay, and mass m. Now I gave it some speed, okay, and because of this it went into a circle, and let's say its time period, it's omega. Okay, if omega is independent of speed, then also notice that time period, which is 2 pi by omega, even this is independent of speed. Okay, and this will turn into 2 pi m by qb. So both of these things are independent of speed. Okay, let's see how. So I threw a particle with a speed, let's say v1, and it ended up moving on a circular motion with a certain time period. Now what if I reduce the speed? Will I still get the same time period? Like in whichever time this particle is completing the circle, if I make it slow, it will still complete the circle in the same time. But the key point here is to note that the radius will be smaller, because radius is dependent on speed. M, Q and B are same. So if you reduce the speed, the radius also becomes small. So now the particle would be moving on a smaller circle. So yes, it will cover the circle in the same time. If you further reduce the speed, it will move in a further smaller circle. If you increase the speed, it will move in a larger circle. It will move in a larger circle. But in all of these cases, the time period will remain the same and the omega will remain the same. So I hope you get this idea that when you are throwing with a larger speed, it is traveling a larger distance, and when you are throwing with a smaller speed, it is moving with it is traveling a smaller distance, and therefore the numbers are such happening, or the things are so related, that the time period is coming out to be a constant value. Okay, so time period is independent of the speed with which we project the particle. All right, okay, so this is about circular motion. Now let's try some questions on circular motion. Let me give you a question on circular motion. So let's try this example. Okay, so let's say this is a region of space. Here magnetic field is 0, but on this side magnetic field is non-zero. Let's say it is B naught. Okay, let's say it is B naught. So let me depict what I am saying, that here we have magnetic field. Okay, here we have magnetic field, and here also we have magnetic field up to a certain distance only. So this is a region of width d. This is a region of width d in which magnetic field exists. There is no magnetic field to the left of it, or there is no magnetic field to the right of it. Okay, all right, so this is the scenario. Okay, so this is the situation. Now imagine, guys, a particle is entering into this region of space. Ignore gravity, there is no gravity. Okay, so let's say a particle with a charge q, mass m, and speed v naught enters into this region of space. Can you imagine, like, can you think about what will happening? Like, the moment it enters, it will start experiencing a force perpendicular to the velocity. Okay, the force will act upward, so the center of the circle may lie somewhere here, and the particle will start moving in a circle. Okay, so the particle will start moving in a circular trajectory. Now, there are two things that can happen. I hope you are able to judge. If d is greater than r, all right, that means if d is greater than mv by qb, then the particle will complete the circle, semicircle, and will go out. All right, and in this case we will say that the deviation in the particle is 180 degree. It is going back from where it came. Okay, so the final velocity is parallel to the initial velocity but in the opposite direction. Okay, so in this case deviation will become 180 degree, and we can talk about other things such as how much is the time spent by the particle in this magnetic field. The answer would be half of time period. Okay, so that is one thing. Okay, that is one thing. Hi Shah Abdullah. Okay, now the other thing is, what if, okay, what if d is smaller than r? That means the radius is too large. Okay, for example, let's say instead of this as the radius, let's say the radius is, this is the radius and like this. So is it clear to you that here the particle will emerge out and then it will start traveling in a straight line? So now the deviation is not 180 degree, it is not 180 degree, and to calculate the deviation we'll extend it backwards, and this will be called the deviation, and this will be called the deviation. So how do we find this deviation now? Okay, so what you can do, you can connect this center to this point where the particle left the magnetic field. So even this is r, even this is r, and if you see this point, from this point we are having two tangents. Okay, we are having two tangents on the same circle. Okay, which basically means that this point, this point, this point, and the center, these 4 points must make a cyclic quadrilateral. Okay, that means this angle will be 90 degree and even this angle will be 90 degree, and if this is delta, this will be 100 minus delta, and then this will be delta. So from geometry we will be able to prove that whatever is the deviation is same as this angle, and now this distance is d, this distance is r, so we can write sine of delta is equals to d by r, and from here we can calculate the deviation as sine inverse of d by r. So like this you can get the deviation in this case. And then if the question asks about how much is the time spent in the field, okay, how much time was spent by the particle, so the time spent in the first case, okay, that would be pi by omega, and in the second case it would be delta by omega. Okay, so we know the angle, we will divide with angular speed, and that will give us the time spent by the particle in the magnetic field. So you can solve these questions like this. All right, getting this? A good question, a very good question, and if you think about it, you will learn a lot. Okay, now let me give you another question. Okay, let me give you a mathematical one this time. Okay, so let's say we have 3 particles: alpha particle, a proton, and a deuteron. So we have an alpha particle, we have alpha particle, we have a proton, and we have a deuteron. Now what are these particles? So in case you are not aware, let me just tell you quickly. Alpha particle is a particle in which there are 2 protons and 2 neutrons. Okay, a proton is simply a proton. Okay, and a deuteron is one of the isotopes of hydrogen from which we have removed an electron. So it's basically a particle in which there is 1 neutron and 1 proton, which means that if we write the mass of proton as m, then the mass of deuteron will become 2m. Okay, and the mass of alpha will become 4m. Okay, the mass of alpha will become 4m. Okay, and if we write the charge of proton as plus E, then the charge of deuteron would be again E, and the charge of alpha particle would be 2e. So we know about the mass and the charge of the particles. Okay. All right. Now let me finish my question. So we have three particles, and these three particles are executing circular motion in a uniform magnetic field. So, okay. So these three particles are executing circular motion. Are executing circular motion in uniform magnetic field, okay, under influence of magnetic force only. There is no other force. Also ignore their mutual interaction. So they are not influencing each other. They are not exerting any force on each other. They are so far apart. Magnetic field, our magnetic field is present in a very large space, and these particles are moving far away from each other or are executing circular motion. So you can ignore mutual interaction. Okay. Now, what do I want you guys to do? Think over this. Here's the question. So find R alpha is to R proton is to R neutron. So you have to find this ratio if all move with same. If all move with same. Okay. First, मेरी आवाज कम आ रही है? Really? Yes, Tanishq, it would be. Okay. If it moves with, let's say, same speed, momentum, kinetic energy, or if they have been accelerated by same potential difference. So under these four conditions, we have to calculate this ratio. Okay. All right. So meanwhile, while you guys are trying this question, let me first take an opportunity to talk about the SEHSS batch. So guys, this is a batch which is for SEHSS examination. If you don't know about this examination already, I would recommend you guys watch video on this. Nidhi ma'am has taken a lot of video explaining this exam. This is the inaugural edition of the exam. Like the first time this exam is going to happen, it will happen in the month of November. I think 30th November is the date when this exam is going to happen, and it is an exam in which PCMB, all four subjects will come. Okay, and we have launched a batch where we are going to prepare the students for this particular examination. The syllabus is up to grade 10 level. Okay, so physics, chemistry, maths, and biology of grade 10 level. Okay, and any student can write this exam. No conditions as far as the grade is concerned. 7th grader, 8th grader, 9th grader, 10th grader, anyone can write. And we have launched a batch where we are preparing the student for this exam. Lots of benefit of appearing in this exam. And more benefits if you qualify, if you achieve some kind of success in this exam, more benefit. But even if you don't achieve any success, the fact that you prepared for this exam will propel you in a very better position. It will, catapult your journey, your academic journey of, securing a seat in prestigious colleges in India. So you will get a head start. All right. So you must, join this batch. You should prepare for this exam. All right. So we will give you regular tests. Around 120 live sessions are planned. Okay, and of course Nidhi ma'am is personally monitoring this batch. So you can join this batch, guys. The link of the where you can join this batch is present in the description of this video, and the price is 10,000, but of course you don't have to pay this. Okay, you don't have to pay this. You can enroll in this batch at this price, 7,999, and this is for the first 50 seats. Okay, after that the discount coupon will become inactive. The discount coupon is this SEHSS20. All right, so avail this scholarship, make use of it, and join the batch, everyone. All right, now let me continue. Let me continue with the question. So the question was that we have to find R alpha is to R proton is to R neutron. All right, if the speed is same. So let me first solve the speed case. So I will first observe my formula mv by qb. Now V is same for all the particles. The question is suggesting this. B is also same for all the particles because they are moving in the same magnetic field. Okay, so when I say that I want to take the ratio of R alpha is to R proton is to R deuteron, it basically means I want mass of mass of alpha by charge of alpha is to mass of proton is to charge of proton is to mass of deuteron divided by charge of deuteron. And now we know all these numbers, so we'll put this. So mass of alpha was 4 times of m. In fact, you can avoid writing m because m will get cancelled, but this is the first case, so let me do it. So 4m divided by 2e, okay, is to mass of proton is 1m, okay, and charge is 1e. And then for deuteron, the mass is 2m and the charge is 1e. So now you can see that m and m gets cancelled, e and e gets cancelled, and then this is 2 is to 1 is to 2. So for the same speed, the ratio would be 2 is to 1 is to 2. Okay, 2 is to 1 is to 2. All right, and yeah, I'm running out of time, guys. So let's just quickly finish this question, and then we'll continue this in the next session, because at 7:30 p.m. Nidhi ma'am is doing a batch launch, and that is very, very important. In fact, any of you, if you are watching this session right now, I would want you to switch tabs and move to that session at 7:30 p.m. not right now. Okay, so this is first part. Now let me quickly finish the second part. Second was same momentum. Okay, same momentum we talked. So now I will write R as mv by qb. Now mv product is same, b is same, so the radius will only depend on charge. So R alpha is to R proton is to R deuteron will become 1 upon charge on alpha, that is 2, charge on proton, that is 1, charge on deuteron, that is also 1. Now if I multiply all the numbers by 2, I get 1 is to 2 is to 2. So this would be the answer to the second part. Okay, similarly we can go for the next part. Next part was same kinetic energy, I think. So radius is root 2 mk divided by qb. Now here 2 is a constant, k is same, b is same, so root m by q. This will determine what the ratio would be. So R alpha is to R proton is to R deuteron. This will become root of 4 divided by 2 is to root of 1 divided by 1, not root. Okay, and is 2. For deuteron, it is mass is 2 and the charge is 1. Okay, so ultimately it becomes 1 is to 1 is to root 2. Okay, so that is the third answer. And if we come to the fourth answer, which was accelerated through same potential difference. Okay, accelerated through same potential difference. Then in this case, we will write radius as root 2 mq delta v by qb. Now 2 is same, delta v is same, b is same, and if I take q within the root, it becomes root of m by q. Okay, root of m by q. So root of m by q. So see, our first answer was m by q ratio. Now it is root of m by q ratio. So whatever you got in the first answer, just put root over there. So your fourth answer would be, like, you can directly write answer as root 2 is to 1 is to root 2. Are you able to observe this? This is root of m by q. So that will decide the ratio. Here we had only m by q. So if I got the answer as 2 is to 1 is to 2, now my next answer would be root 2 is to 1 is to root 2. Alright guys, I wanted to cover more, but let's end it here, because Nidhi ma'am starting her session regarding the batch launch. So I'll see you in the next class, guys. I'll cover the third possibility, which is the general case in which the trajectory of the particle is a helix, a spring-like figure. So we'll do this in the next class, everyone. And thank you for watching this session. I hope you like this. Of course, it was a very power-packed session. We covered a lot of things very quickly. But then I feel that the button for speed is in your hand. You can slow it down. You can repeat whatever you want to see. So therefore, I can take the liberty to go a bit faster. See you next week, everyone. Take care and bye-bye.